Assalamualaikum and a very good day to all of you. Presenting a video presentation from group P20S20 with title Numerical Analysis of Smoking Model using Runge Kutta for Order Method. The presenters are Hazwani binti Mahyuddin, Nadia Afika binti Azhan and Nur Shazwani binti Muhammad Yani. This group is under the supervision of Dr. Nur Azni binti Shahari.
There are 10 parts for this presentation, which are introduction, problem statement, objective, significance of the project, scope and limitation of the project, literature review, methodology, result and conclusion, and recommendation.
First of all, let me share with you some information about smoking statistics. The World Health Organization has estimated that almost 10 million deaths each year will be caused by 5.6 trillion cigarette smoke per year at the end of the 20th century. There are few groups created from smoking population such as passive smoker and relapse smoker. Person who inhale secondhand smoke is called passive smoker. Whereas, person that have attempted to stop smoking and they have potential to smoke again is known as relapse smoker. Mathematical modeling plays an important role in modeling the regulation and spread of many diseases, including smoking. There are two ways to model smoking model, such as differential equation and fractional derivative differential equations. There are many methods that have been used to approximate the giving up smoking model. As in our study, we use Runge Kutta method to solve smoking model. Runge Kutta method is one of the most recommended numerical solution for differential equation. This study will determine the difference in behavior of smoking population using two different models. The first model is analysis of mathematical smoking model studied by Puroisio Montoya in 2019, and model 2 is stability or an analysis of chain, mild, and passive smoking model studied by Asharif and Batarfi in 2020. For the problem statement, most of the research in the smoking model discuss and identifies the global and local stability of the model without comparing it to any other smoking model, and they also do not make any comparison between other smoking model.
For the first objective, to identify the behavior in the presence of tobacco consumption between the different type of smokers population by using RK4. Second, to evaluate the effect of both of the chain smoker and mild smoker separately on the exposed population using modified giving up smoking model. Third, to determine the effect of the population behavior when the value parameter has changed. In this project, the numerical method, which is RK, was proposed to solve the system. Smoking models can identify the effect of smoking toward exposed population. This project not only focuses on identifying the effect, it also can make comparison between smoking models. The result will show the different behavior of the smoking population in the presence of tobacco consumption between both smoking models. We focus on numerical analysis of a giving up smoking model using RK4. The data information will obtain from these two models, which is Model 1 and Model 2. This study also find the point of the equilibrium and the basic reproductive number. Then, this study will do the calculation process using RK4 and solve it using MATLAB. Lastly, this study compared these two models to get the most practical model for giving up smoking model.
Many researchers have modified and developed the smoking model. Oluwaseun Sharumi Abah Bigumel modified the smoking model by adding the compartments of the mild smokers and chain smokers in 2008. In 2011, Gulzaman expanded that ex-smokers may smoking again and use optimal control theory for smokers' optimal problem. In 2018, Anwarzeb, Ayesha Bano, Ibrahim Al-Zahrani and Gulzaman considers the dynamical behavior of the smoking model within the type of delayed differential equations. Many methods that have been used to approximate the smoking model. In 2012, Anwarzeb, M. Ikhlaq Shohan and Gulzaman used homotopy analysis transform method. In 2013, Hai Feng Huo and Chen Chengzhu used Lyapunov method and Ruth-Hurwitz theory. Next, Samia Bushnak, Banan Maya and Asma Al-Habis used reproducing kernel Hilbert space method in 2016. The methodology of this study consists of three main phases. We want to highlight the mathematical formulation, which is the most important component in this study. These are the state transmission diagrams and non-linear differential equation for Model 1 and Model 2. From this equation, the numerical equations for Model 1 and Model 2 have been solved using MATLAB. Next, let's proceed with result and discussion. Six values of parameters have been used throughout the study. They are two sets of values for beta, eta, and alpha, where are not less than and equal to 1 and are not more than 1. Three sets of initial conditions for both Model 1 and Model 2 also used to determine the result. The first result shows behavior in the presence of tobacco consumption between the different types of smokers population. From the graph of Model 1 with R not less than and equal to 1, it can be seen that the rate of passive smokers and smokers decrease over the time. For relapsed smoker, it increased until it reached the peak, then decreased. From this graph, we can conclude that all the smoking population reach an equilibrium point as time increase. For Model 2 with R0 less than and equal to 1, it gives almost the same result as Model 1. The only difference is that the smokers have been divided into chain and mild smokers. Generally, this graph shows a difference between the rate of the chain and mild smokers. The chain smokers have higher probability of generating more new smokers because of the dependent parameter in the equation. We also analyzed the equation with set of values from R0 more than 1. The rate of passive smokers decreased rapidly while chain and mild smokers increase until reach their maximum and then decrease. The chain smokers have higher probability than mild smokers, same as the graph before. The rate of relapse smokers increased, then it remains same when the number of chain and mild smokers decrease.
Based on the graph, this study used 3 initial conditions to make comparison between Model 1 and Model 2. This graph compares between smokers with chain smoker and mild smoker. This shows that the rate of smoker is the higher compared of chain smoker and mild smoker in Model 2. The rate of relapse smoker in Model 1 is higher than the rate of relapse smoker in Model 2. This is because the relapse smoker are exposed to smokers' community. The maximum value rising rate of relapse smoker can be reduced when the interaction occurred between chain smoker and mild smoker instead of smokers. The graph shows the changes of equilibrium point on passive smokers. Formula of equilibrium for passive smoker is delta divided by D1. There are 3 different values of delta that we show on the graph, which are 70, 50, and 30. It shows different equilibrium points corresponding to the different value of delta. The equilibrium point of delta 70 is the highest because the average number of healthy people that have potential to become active smokers also the highest. In conclusion, the lower value of delta, the lower equilibrium point will get. Hence, it will give the lower rate of passive smoker.
Here, effect of behavior of smoking model with different value of factor that change smoker related to mild smoker to become new smoker, which is also known as eta. There are 5 different values of eta are used in this part, which are 0, 1.0, 1.5, 2.5, and 3.5 to see the effect on smoking population. When the value of eta increase from 0 to 3.5, we can see that the number of passive smoker keep on decreasing while the rate of chain and mild smoker become higher. For relapse smoker, the maximum rate increase as the number of eta increase from 0 to 3.5, but the rate then decreased to its equilibrium point. However, we can see that the rate of chain smoker is higher than mild smoker. Here is the result of comparing the different values of probability of exposed people become either chain smoker or mild smoker, known as alpha, and its effect towards smoking population. There are 3 different values used in this section, which are 0.2, 0.4, and 0.6. The changing on values of alpha does not give effect to the rate of passive smoker and relapse smoker. This is because the parameter alpha do not exist in the passive and relapse equation. Therefore, the changes value of alpha will only affect the chain and mild smoker, as we can see. At a constant time t equal to 3, the rate of chain smoker keep on rising as value of alpha increase, while the rate of mild smoker keep on decreasing. As a result, the tendency of exposed population to become chain smoker is higher. Now, we will see the difference effect of infection rate, known as beta, towards smoking model 2 with R0 less than and equal to 1 and R0 greater than 1. There are 4 values of beta used in this section, which are 0.02, 0.05, 0.2, and 0.5. For this model, where R0 less than and equal to 1, the rate of passive smoker are decreased as the rate of beta is increased. The rate of chain and mild smoker keep on increasing as the infection rate increase. However, for the relapse smoker, the rate is increased until it reaches its maximum value at beta equal to 0.22. Then the rate of relapse smoker will decrease. However, the equilibrium point will increase after beta equal to 0.2. Nonetheless, when the value of beta is increased to 0.5, the rate of relapse smoker become decreased. Here is model 2 where R0 more than 1. As the value of beta increase, the rate of passive smoker become decreased. While for chain and mild smoker, the rate is keep on increasing as the value of beta increase. While for relapse smoking population, the rate keep on increasing as value of beta increase. However, when the beta equal to 0.5, the rate of relapse smoker decrease. So there are some different effects in changes of value beta towards smoking population in R0 less than equal to 1 and R0 greater than 1. For R0 less than equal to 1, mild smoker reach the highest rate compared to R0 greater than 1. While for chain smoker, R0 greater than 1 have the highest rate compared to R0 less than and equal to 1. For passive smoker, R naught greater than 1 have the lowest rate compared to R naught less than and equal to 1 as the number of beta increase to 0.5. This shows that the R naught greater than 1 have more tendency to be infected if value of beta increase as the rate of passive smoker decrease with a huge value compared to R naught less than and equal to 1.
For the conclusion, from this study, firstly, we can conclude that Model 2 gives a better solution for smoking model compared to Model 1. This is because Model 2 divides infected population to chain smokers and mild smokers. Second, it showed that when we use the same initial value on Model 1 and Model 2, chain smoker and mild smoker give less effect on the infection rate towards smoking population compared to smokers. Lastly, it can be concluding that the less interaction between mild smoker, chain smoker, passive smoker and relapsed smoker population over the time, then the number of smokers group decrease, thus it reach equilibrium point more rapidly.
For recommendation, add parameter of alpha to passive equation. This is because alpha is equal to probability of exposed people to become either chain smoker or mild smoker. Hence, we can know the effect of passive smoker towards changes in value of alpha.